In this video, we're going to move on to section 6.3, which is all about Taylor series. Taylor, and if you want to call them distinctly, Maclaurin series. And I'm not sure if I'm saying that correct, so don't quote me on that. The definition: if f has derivatives of all orders at x equals a, then the Taylor series for the function f at a is the sum from 0 to infinity of f, the nth derivative of a, over n factorial times x minus a to the n. Right, and then we can write out a couple of these terms, right? The first term, this n is going to be 0, so that whole thing is going to go away, right? So the first term just simplifies to f of a, right? The 0th derivative is just the function itself. Then we have the first derivative at a, and then one factor, remember, is just 1. And then we have x minus a to the first power. And then I'm going to write the third term down here. When we plug in n is 2, we get the second derivative at a over 2 factorial times x minus a squared, and so on and so forth. And then for the Maclaurin series, for f is the Taylor series when a is 0. So literally the Maclaurin series, all you do, like, we can literally just so I can emphasize this, I can literally just copy this formula and change all of these a's, change all of these a's to 0, and that will be the Maclaurin series. So don't overcomplicate that at all. Right, and obviously we don't usually write minus 0 because that doesn't really mean anything. So this just ends up simplifying to the nth derivative at 0 over n factorial times x to the n. Right, so we have f of 0 plus f prime of 0 times x to the first power plus f double prime of 0 over 2 factorial times x to the second power, and so on and so forth. So the same way that we used partial sums for infinite series, we'll use them in a way for Taylor series. So basically what we do is we come up with a bunch of Taylor polynomials, and that's the fancy name for the partial sums for Taylor series. So the nth partial sum of the Taylor series is known as the nth Taylor polynomial. right? So what does this look like? Literally, remember, what is the nth partial sum? That is when we take this infinity, right, and we change it to n, right? So we sum up to a specific number. So we take the infinite sum and we make it finite. So that's what we're doing here. So if f has n derivatives at x equals a, then the nth Taylor polynomial for f at a is, and the notation we use is p with a subscript x denoting the nth Taylor polynomial. And then, right, we do the same thing. It's just like the first n terms of the series. So, right, we had f of a plus f prime of a, x minus a plus f double prime of a over 2 factorial x minus a squared. And then I need to keep this going all the way until I get to the nth term, which is the nth derivative of f at a over n factorial times x minus a to the n. Right, and so if we wanted to simplify, like in sigma notation, right, like I said, it's just changing that to a finite number there, and we still use the same formula. Right, technically this notation is a little off because we're going from n is 0 to n, but right, so this could be like a k, and this would be pkx. Okay, so, and then again, when a is 0, these are Maclaurin polynomials. So literally everything translates from Taylor series to Maclaurin series, because literally a Maclaurin series is just a Taylor series with a equals 0. So it's really just a special case. Okay, right, so let's talk about the partial sums and how all of this works. Right, so our definition for Taylor series is here, and let's do like the first 4 partial sums of this. So we're still talking about Taylor polynomials, because remember, Taylor polynomials are equivalent to the partial sums for Taylor series. All right, so for example, the 0th, first, second, and third partial sums of the Taylor series are, right, so for P0, remember that that means that we only take the 0th term, so we do the sum from 0 to 0. Right, so the only n I get to plug in is 0, which is f0 of a over 0 factorial x minus a to the 0, which remember, like I said, the 0th derivative is just the function itself. We know 0 factorial is 1, anything to the 0 power is 1, so this is just f of a. P1 of x is going to be the first two terms. So the first term I got was f of a. Now I need to add in when I plug in n is 1. Not n, right? N is 1 here. So P1 of x simplifies to f of a plus f prime of a times x minus a, right? Because we know that 1 factorial is also 1. And then P2 of x, right? Now we bring down those first two terms, and then we have to plug in when n is 2. So that becomes the second derivative at a over, 2 factorial times x minus a squared. And then lastly, for the third one, I'm gonna have to try to write smaller. Right, I bring down everything from P2, those first three terms, and then I need to just plug in n is 3 for the last term in the third Taylor polynomial. So pretty, hopefully straightforward, right? And so right, like this is the 0th Taylor polynomial, the first Taylor polynomial, the second Taylor polynomial, and then this last one is called the third Taylor polynomial. Just for vocab, right? This is the first Taylor polynomial. This was the 0th Taylor poly, right? And so on and so forth. And then again, if we let a be 0, these would all be called Maclaurin polynomials. So all of this we can bring over to the Maclaurin side. So let's do an example finding some Taylor polynomials. So find the Taylor polynomial nulls P0, P1, P2, and P3 for f of x equaling ln of x at x equals 1. Right, so the first thing we need to notice, right, well, remember our formula for the Taylor polynomials we had was Pn of x is f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a squared plus, right, we go all the way down to the nth term. So great, I'm out of space. X minus a to the n. Right, so then to find all of these, right, we're going to need the first derivative, the second derivative, all the way to the nth derivative, right? In this case, the highest derivative we're going to need is 3, right, to find that third Taylor polynomial. So note that we need to find f of 1, f prime of 1, f double prime of 1, and f triple prime at 1 in order to get P0, P1, P2, and P3. Right, so our function f of x is ln of x. We know when we plug in 1 into ln, we get 0, right? Because we have to raise e to the 0 power to get 1. That's the relationship between e and the natural log. The derivative of ln we know is 1 over x. And then if we plug in 1 into that derivative, we just get 1 over 1, which is 1. And then if we do f double prime of x, right, we would see this as x to the negative 1, and we would do a power rule on it. So we would get negative x to the negative 2, so that's negative 1 over x squared. Get rid of this for clarity. And then if we plug in, oops, drop my iPad. Okay, so if we plug in 1 into our second derivative, right, that's negative 1 over 1 squared, which is just negative 1. So I'll just clear up all the scratch work. And then if we do the third derivative, right, we see the second derivative as negative x to the negative 2, so that would be negative 2 times negative 1 becomes positive 2, and then over, right, we would have x to the negative 3, which I could just bring down to the denominator. And then if I plug in 1 into that third derivative, I would get 2 over 1, which is just 2 itself. Okay, so remember, this is our formula, right? This is our formula for the Taylor polynomial. So the first one is just the first term, right? So P0 is equals just to f of 1, which we got is 0. And then P1 is that term that, right, it's going to be the first term, f1, plus when we plug in n is 1, which is just the first derivative at 1 times x minus 1. Right, so that's going to simplify to 0 plus f prime of 1 we got was 1 times x minus 1. Right, so then P1 is really just equals to x minus 1. And then P2, right, we bring down all of these terms from P1, but now we have to add on the n equals 2 terms, so we get the f double prime of 1 over 2 factorial times x minus 1 squared, right? So then that all simplifies to 0 plus we got that P1 was, well, this term here, right, was just x minus 1. Oops. And then f double prime of 1 we got was negative 1, so we're going to plug that in. And 2 factorial we know is 1 times 2 is 2. And then we have x minus 1 squared. So let's simplify this, and P2 is then, right, x minus 1 minus 1/2 x minus 1 squared. And then finally, the last but not least, we do P3, right, which is all of those terms that we already had for P2. And I'm just writing out the formula just for like completeness sake, so you guys can see it, since this is the first time you're seeing it. So now we plug in n is 3 for the last term. And then, right, we bring down everything we had from before, from P2. And now we add on, right, now we know f triple prime of 1 we got was 2, so that's going to be 2, and then 3 factorial we know is 6, and then we have x minus 1 is 3. Right, so then P3 simplifies to x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. So, right, it didn't ask us to come up with a formula of Pn, right, but I feel like it's good practice, right, because we can see a pattern here, right? So for the very first term, right? Like what we can see is the terms look like this would be 1 over n times x minus 1 to the n. And here we would need to start n at 1. So that's how we're going to end up finding formulas for the nth Taylor polynomial, which will be the series expansion for the function itself, right? Okay, so I think I'm gonna do 2 more examples in the next video. So 2 more examples in the next video. All right, I'll see you guys there.